Hi, my name is Shravan Romanov,
I'm Andrew Frels.
I'm Ravi Pawar,
And I'm Caitlin Schmeiser.
and this is our BME 206 ACL design project. So the ACL, or the anterior cruciate ligament, is the ligament that connects the tibia to the femur in the knee. The ACL provides knee support, and each year there are almost 100,000, 200,000 injuries just in the US. Injuries for the ACL occur from abnormal leg and knee movements, such as random jumps, cuts, or abnormal stops. So currently there are three different graft methods. An allograft is from another person or donor. An autograft is a donation from other ligaments in yourself, and xenografts are artificial or non-human grafts. The downside to current grafts is that it can leave other areas compromised of function. In addition, a current healthy ACL has strength in the magnitude of kilonewtons and a 10% elongation failure. Additionally, an artificial ACL currently can have a strength of about 1,500 to 3,000 newtons, but this number changes when taking into account outside factors. You also have to look at recovery time and strength decrease. Our design proposal was developed to identify a way to provide increased stability to the ACL and surrounding ligaments. We will look to rectify ACL tears associated with sports-related injuries at both an amateur and professional level to reduce the number of recurring injuries and stress in a timely manner. So for our improved artificial tendon, our ideal dimensions imitating a natal ACL would be 30 to 40 millimeters squared with cross-sectional area and 40 millimeters in length. The minimal tensile strength at yield would be 1,500 newtons, and our minimal elongation would be 10 to 15% at yield. In addition, we also want to ensure that there's cytotoxic compatibility. When looking at our transplant site, obviously the ACL is associated with the knee joint, so we want to ensure that it's inserted in a way that provides maximum stability. In addition, we need to account for the fact that there will be multiple different cell types as well as non-cellular components that we need to take into account. And in terms of other properties, we also need to look at the lined fibrous tissue in the knee as well as the density of the site.
Objective. The objective of our study is to assess the feasibility of NinjaFlex as our material in an artificial ACL implant. Further, we'll look into the answer to the question of how similar are the physical and biological properties of our implants is to a natural ACL. Implant device description. Our choice of material was NinjaFlex, and we chose this because we thought it was the most compatible because of its high tensile and bending strength. Our ligament would attach the tibia and femur through small drilled holes fastened with screws and cement. This ligament also ride on the extent groove of the knee in order to replicate an original ACL. So here are some of the characteristics we're kind of looking for. We would like a linear load from chemical properties, Young's modulus of 128 MPa for male and 99 MPa for females, as well as an implant strength of 1,500 newtons for yield and 2,000 newtons for failure. This next page is our drawing of our ACL implant design that we used, that we CADed in Fusion 360. And what are some of the benefits of our 3D printed design? Well, number one is that it is 3D printed, which means it can be customizable to patients. There's easy design iterations that can be done, as well as its ability to be reproduced. Another benefit is that no other tissue, internal tissue could be damaged. That meant from an autograft, we wouldn't have to be taking a graft from another part of the patient's body. And the biggest one is that it's cheap and readily available to everyone.
Now we're going to talk a little bit about the methods and materials involved in our testing. So first, we did a cytotoxicity test to prove that the material was safe to use in the body. We used the lab procedure given during Lab 6 to perform these tests. The materials we used were NinjaFlex extract, phenol-free media comprised of DMEM, FBS, and PS, Marblue dye, and a 96-plate well. This is the setup we used for our well. We had both positive and negative controls, as well as a variety of extract concentrations to try to find what percentage of extract would be safe to use in the human body. We had cells that had no treatment, cells that had 100% treatment that we were sure was going to kill the cells, And then we also had cells with no medium, or sorry, no cells and only medium to prove that there was no outside contamination.
The next test we did were stress testing. Just a quick reminder of background, a healthy ACL would have a strength in kilonewtons and 10% elongation failure. We would want our artificial ACL would be able to withstand 1,500 newtons to 3,000 newtons. The stress test that we designed adequately mimicked the in vivo motion. We used Lab 2 procedure. You can see that device on the right side of the screen. That's the device that we used in lab to stress test our materials. Continuing on with this stress test, we used 5 type 4 samples of NinjaFlex. So you can see that image in the top, that is the shape of the design that we made. We ran until failure at 50 millimeters per minute. And our test recorded the time, force applied, and distance pulled in order to analyze the stress and strain for each sample.
Now we're going to talk a little bit about the results from our experiments. So here you can see the results of our cytotoxicity test. What we found is that there is no statistical difference between any of the extracts. They were all statistically the same, meaning that they were all negative in their killing of cells, as they're the same as cells without any extract in them. You can see that from the Tuckey test table on the side. All of the groups with A are statistically similar, and all the groups with B are statistically similar. So the groups that were positive, or the positive group and the media group, were all statistically the same, meaning that there was no difference between having no cells in the well and then having only dead cells in the well. And then there was also found no statistic difference between having any sort of cells in the well.
Now onto our stress test results. Here are the stress and strain curves that we generated from our 5 samples. As you can see, they're all very similar, so we had a lot of consistency with their results. However, none of our tests did reach failure, so none of our samples broke all the way. So our testing did not go as far as we wanted to. As you can see in the graph here, we wanted our stress and strain samples to follow this kind of pathway, and we only really got to the very beginning of the run and rise section. So none of our samples reached the maximum or failure, and that made us unable to determine the maximum stressability of the NinjaFlex material. Our maximum stress was 15 megapascals, and that was found by just looking at the maximum that we were able to reach, which would indicate 60 newtons. Here are our conclusions. Our material is chemically valid and not cytotoxic according to our cytotoxicity test. Our stress test was inconclusive and we were unable to find the true maximum stress. We know that it can withstand at least 60 newtons, but we need it to be able to withstand 1,500 to 3,000 newtons according to our background research. Because of the inconclusive stress test, we cannot conclude that this the NinjaFlex material will work fully. Our testing was also too narrow. We had no attachment tests, no shape tests, no torsion or bending tests, and our stress test did not go far enough.
So what we want to do in the future, as Caitlin kind of touched on, is expand what we tested. First off, we would want to verify the full stress ability of NinjaFlex filament. And if we found that it worked and it reached that 1,500 to 3,000 Newton threshold, we would want to then move on to testing the implants and securing the actual implant into the bone. So we could do that either by using a cement, screw, or wedge design. The one that we have drawn up here is a bit of a screw design. We would also want to test common failure modes, be it like the corners of the square design that we currently have, maybe a round one would be better. Are there any strange patient morphologies that would impact how we would implant it? Is there any concerns with long-term stress of the material as opposed to the short stresses we've done? And those are all different kinds of tests that we would want to accomplish if we were to move forward with testing this implant. Here are all of our citations for this presentation. And finally, we'd like to thank the lab TAs for providing assistance and support to our design iterations, as well as the overall project. And in addition, we'd like to also thank Dr. Linus for his continued help in teaching us various laboratory techniques in both BME 205 and 206. Thank you very much.